There we go. So we need to add an extension to this part of the fan, right? That's the entire result of how we can change the flow resistance. Again, it's not the only way to change the flow resistance, but it's, in my mind, probably the best way because you only have to change the geometry once. After that, we can tweak the numbers without needing to remesh or do anything fancy like that. So one way we can do this is we want to, we want to know where exactly this is in space. We are fortunate in that this happens to be perfectly aligned with the universal coordinate system where x-axis is horizontal, y-axis is vertical, and then clearly z-axis is by right-hand rule out of the board, right? So somewhere on here, because this toolbar is collapsed, there should be a ruler tool. There we go. So we should be able to measure from one end of this to the other and see exactly what coordinates they're at. So this outlet is, well, theoretically, actually, let me make this a mesh scene. Mesh. So we can measure exactly where those points are and make sure we get let me be more exact than this. Oh, I know why this is giving me grief. This is in, there we go. Now it's in parallel mode. That makes it so much better. FYI, if you're looking at two-dimensional things, if you see this camera button at the top right, you probably want to put it in the parallel projection mode instead of perspective, because if you have a two-dimensional thing, there is no perspective. But it will still try anyways and make things look kind of weird. So let's try this again. And see what this has to say about it. So it looks like on the x-axis, this is pretty much, well, this is very consistent on the x-axis at least, which is what we need. And the y-axis values are also very consistent. It would have been slightly better if I'd included this block straight out of SolidWorks or whatever, but we can get it really, really close in theory. New shape part block. So we are going to want this block to be, well, both x coordinates should be, or one x coordinate, excuse me, should be exactly this negative 0.13949. Again, I'm not terribly worried about people actively following along so long as you get the concept. And then we want to do a third of a meter, so negative 0.43949. Now for the y coordinate, well, as measured, it's 0.17775 meters, and then I think that's exactly a tenth of a meter, so 0.0777. Oh, excuse me, that's an extra 7 meters. And then Z, one of these can be 0, one of them can be like 1, I guess. So if we create this block, this should line up, if I can zoom in here, basically exactly. Let's take a look at this. So if we look at the top here, there might be a very slight step, but it's only microscopic in nature. It's actually... Yeah, this is probably close enough, although we might be able to fine tune it a little bit. Let's see here. One thing we can do is if we right click on the block, we can say edit part in current scene, and we can tweak the Y values. So hopefully they match slightly more exactly.
Could you also use the snap to part?
No, not really, because the entire fan is one part.
You can, if I use it, then it's useful. You just only make it like out.
Oh, there we go. It looks like that.
It does bother me. It's actually should,
Oh, you can snap it directly to the outlet size.
yeah.
Oh, let's give that a go. But I think that is actually the right size. Exactly. But let's go ahead and snap it to the outlet and see what it works. See how that works. So if we, sure, I guess the air stator, and we have not that one. This blower fan 1, I think, is it, right? If I'm remembering correctly. Why won't this let me select anything? Oh, it has to have a volume to it?
You just go press the arrow on the block. Arrow.
Oh, yeah, there we go. Oh, outlet, there we go, yep. Although, incidentally, it still didn't snap exactly.
Get another thing selected.
I think I only had one thing selected. Air stator, subtract, blower fan, outlet. I only had one thing selected. It's really, really, really close, don't get me wrong. It's almost certainly close enough, but I'm going to go with exactly the number I had earlier, which was 0.1778 and 0.0778, and then it's 1/3 of a meter long.
You have to move the x-axis still. Because,
Yeah, it's slightly off.
how about the corners? Because both x's are the same.
They should be the same.
What x value?
This is a planar face.
But then the block has to change it.
In truth, we're probably not going to get this to exactly fit no matter what we do. Oh, actually, I should not have done that. 0.1, but we can get it really, really close, which should be enough for this application. All right, so that only adjusts that way. Yep, CFD can be properly finicky pretty much no matter what. 3.9, so 3.95, 3.96. Oh, right, one of these needs to be 4. You're right. Sorry, negative 0.0. one. There. That's as close as it's going to get, I think. And again, it should be really, really, really close, which it is. It does not necessarily need to be completely one node on top of the other because there is a tolerance to the interface, you'll recall. It does have a small tolerance on the order of, 1/10 of a millimeter or so. So as long as we're well inside of that tolerance, we should be fine. But we need to go through all the same process. We need to split the surface of this block into several pieces. We need to create a contact between the rightmost face, which is hard to identify in this scenario, unfortunately. Let's see here. Because it says both face 4 and 6 could be it, right? In this case. So which face is the rightmost one? It's 6. So 6 is the one that we need to make a contact with. It's a little bit hard to see. Let me zoom in some more. You see the highlighted face? So this is the face that's touching the fan. So we need to make a contact between this and the fan outlet. We know that is part of the air in the stator region, which so we can select the two surfaces and create weak in-place contact. It's not ideal, but it definitely is important here. Well, actually, hold on a second. We can probably add this to our existing operation. Because the very last thing that why did it just minimize everything? There we go. In operations, I think the last thing we did was, well, we meshed. But before we meshed, we imprinted. So if we add our block 2 to the imprint, it should theoretically find a contact. Yep, there is a contact between the air stator and this block right here. So you can add your block to the imprint and it works just fine. Which is the better way to do it because it's automatic. If you need to redo anything later, it will recreate the contact. We do need to remesh and all that other good stuff, but we need to add our block to the badge for 2D meshing. And we probably also want to add it make the badge for 2D mesh again. We also want to add it to our mesh node. So I think I already know exactly what this is going to say, and I also know how to fix it, but I'll let it mess up so we can see how it yells at you. And then we can go back and fix it later. So we added a block, just to run through a checklist. We added a block. We made a contact between that block and the outlet of the fan. We told it to go ahead and turn this block into a two-dimensional simulation plane. That was the badge for 2D meshing part. And now we're almost ready to mesh it, but we need to make a new region for the block specifically. So we're going to assign just the block, because we already have a region for all the other parts. Just the block to a new region. is it? Regions. And now we have a extra domain. And we can see that it has a right-hand side, a left-hand side, a top, and a bottom. The top and bottom are walls, that's fine. The right-hand side is an interface. It hasn't actually done the interface math yet, but that right-hand side does have an interface there, which is good. So we have an interface between this block and the outlet of the fan. We have the top and the bottom, and we want this one on the left-hand side to be our new outlet. So I'm just going to make this a pressure outlet. And we need to get rid of our old outlet because that is no longer an outlet. Theoretically, it shouldn't exist at all anymore once this interface happens. But just to make sure we don't accidentally have a pressure outlet kicking around, we're going to turn what was our old outlet into a wall. There is an interface there, though. Yeah.
I have a question. Why would it create a problem? Isn't it just spewing out from this outlet to the next outlet?
If you have a tiny cell, so if we zoom way the hell in, it could conceivably have a tiny cell right where the old outlet was on the right-hand side and the new outlet on the left. It could have a cell that doesn't quite connect. And air would be allowed to leak out through that cell if we left it as an outlet. If we make it a wall, then no air is allowed to pass through it. So you literally might have a leak in your fan if you left that as a pressure outlet, which it probably wouldn't be big enough to cause any serious problems. But it's simple enough to fix. Just change it into a wall and you eliminate that problem. So you'll generally, as a rule of thumb, you only want one inlet and one outlet. If you have extra things being an outlet that shouldn't be, it's going to screw things up more than a wall will.
That change it into a wall will stop the flow.
If you theoretically, if it wasn't connected at all, then yes, it would stop the flow. But at that point, you've already failed because they're not connected at all. So the thing is, if only a little tiny piece of it is a wall, that's not a problem. It's the equivalent of having a bump on the surface instead of having a hole just venting to atmosphere. So it is still kind of a problem if some of those cells don't imprint properly, but it's more of a problem if they're an outlet. So in this case, we're changing it so we have only one inlet. This circular face over here, cylindrical face, only one outlet. That's it. The outlet that used to be here has been moved entirely. So this face in between is no longer an outlet. Let's see here. So we have all three of our regions. Now we can theoretically go ahead and mesh this without too much trouble. But I wish I could zoom this in more, but if we select the region itself, in this case it's called block 2 because I haven't bothered to rename it. You might want to rename yours, but if you don't do too much, then it's not the end of the world if you don't. We can change it from a fluid region under the properties to a porous region. You'll see the icon change a little bit. It puts like diagonal hash marks through it. This is like a lot of the symbology in the software indicates that it's a different type of region. It's not a pure fluid region anymore. It's a porous region, which again, the idea of a porous region is that it simulates something like a close packed surface, like a sponge or closely packed fins, or something that provides resistance to the flow. If you have a denser set of fins, it provides more resistance. If you have less fins, it provides little to no resistance. Without changing literally anything, we can arbitrarily make this box without changing its size. We can make it as high resistance or low resistance as we want. There are two physics values that control this by default, and these are the ones we're going to be using. So again, this is the block 2 region under physics values for the region. So let me collapse this. So we have block 2 It has boundaries, it has physics conditions, and it has physics values. Under physics values, we have two values specifically. We have porous inertial resistance and porous viscous resistance. These are how much resistance does the flow experience as a function of how fast is the flow going. The faster the flow is going, it will experience more resistance. Inertial resistance will effectively scale with velocity squared. If your velocity doubles and you only have inertial resistance, your resistance will go up by a factor of 4. Viscous resistance, which is the other one, is a linear change with velocity. So if I'm thinking about this correctly, the equation is something along the lines, did everyone get this concept? I'm going to erase this in a sec. What's up? Is something along the lines of it institutes a change in pressure that is equal to the length of the cell. Chair out of my way. Times the, I'm just going to put capital I for the inertial resistance, times velocity squared plus, I can't really use V for viscous, can I? Okay, I'm just going to use lowercase n for viscous resistance for the moment. Not a generic symbol for it by any means, just we're using n for the moment to represent viscous resistance. Times velocity. So in SI units, the length will have unit of meters. Inertial resistance has units of mass per, so kilograms. Kilograms times meters to the fourth. This will be meters squared per second squared for velocity squared. So I'm just making sure I got this equation right via dimensional analysis. If you're not following why I'm doing this, I'm making sure I got this concept right. What's a pressure? Just conceptually, what are the units of pressure?
Kilograms divided by n cubed, or something like that.
Not kilograms. What is a pressure conceptually? Force per unit area, newtons per meter squared. A newton is kilograms meters per second squared per meter squared. So really it's units of pressure are kilogram per meter second squared. So let's see if this all works out. This is in the numerator, not in the denominator. So it looks like that matches exactly, because this will work out the same. This is the units of viscous resistance are kilograms meters squared seconds, meters cubed seconds, excuse me, times meters per second. So yeah, this does work out. That is how it does it. So it will calculate the change in pressure in any given cell in that area by the size of the cell times the product of the inertial resistance times velocity squared plus viscous resistance times velocity. This lets us change viscous and inertial resistance and get a change in pressure out of it. If we increase these, we get a bigger change in pressure. We decrease them, we get a smaller change in pressure. All right. The exact values aren't as much a concern as we want to be able to move up and down that fan curve's y-axis by changing how much pressure there is. So again, we have two, I say two values. We realistically have, in this case, 4. If this were 3-dimensional, we'd have 6 values. Because this allows you to change the resistance differently in the x and y directions. Any idea why it lets you do that? I'm going to turn off the monitor for the projector for just a second here so I can use the other section of whiteboard. Any idea why you'd want to change the resistance differently in the x and y direction? Well, I mentioned a couple of things that could provide resistance to the flow earlier, right? What things did I mention?
Multiple things.
What are the examples I gave?
Oh. Sponge.
Sponge is one of them. Now, that theoretically looks pretty much the same no matter which way you go through it, right? It's not perfectly regular, it has irregularities, but whether you're going one direction through a sponge versus, sideways relative to that, it's probably roughly the same resistance. In something like that, you wouldn't need different resistances in different directions. But what was the other case I mentioned?
If you have like multiple fins stacked, then if you're like, if the fins were face down.
In general?
Yeah.
Fins. Well, okay, if you have a whole bunch of fins, it's going to be slightly difficult for air to move that way through them. It's going to be very difficult for air to move that way through them, right? Theoretically, air just straight up shouldn't be able to go that way at all, assuming these are solid, right? In practice, if we have something like a sponge, then, my computer is completely resized based on resolution, but that's okay. If we have something like a sponge and we fill a block with it, our resistance in the y direction and the x direction is going to be the same. So our I x will equal our I y. Ditto our viscous resistance, right? It'll be the same in both directions for something like a sponge. For something like fins, on the other hand, these will not be equal to each other. If our fins are aligned this way, which resistance is higher? X is horizontal. Which resistance is higher? The fins are running this way. Which way is it easier for the flow to go? It's easier for it to move in Y, which means which one is going to have the higher resistance? Resistance means it's harder for it to flow. So it's reversed. If it's easy for it to go in the Y direction, you have much higher resistance in X. Again, theoretically, if these are solid, there is absolutely no resistance, or there's no way for flow to move in the X direction. But we tend to not want to set values to infinity. That generally makes computers unhappy with us. So we don't. What we tend to do in the case of fins, if these are not equal, is that we will say that the X direction resistance is equal to, it depends on what you're doing, honestly, but as an approximation, you say 100 times the resistance in the Y direction. Technically, the simulation will let flow across one of these fins. but it will be really hard for it to do, and it will lose a lot of pressure doing it. So the flow will almost always align exactly with those fins. Because if we make it literally impossible for it to cross here, that can make your simulation numerically unstable. So we make it possible, but only a little bit, if that makes sense. The flow will, again, once it's fully converged, will just be following the y direction. But it's allowed to follow the x direction temporarily to figure out what's going on. But in a nutshell, for this case, we really don't care all that much. We just want a flow resistance, right? We don't need to treat it like fins. We could treat it like fins, but we can, for the intents and purposes of this one, we can instead say that they're equal to each other. I just want to highlight why there are multiple directions to this value, because if you do anything with porous regions and fins, they're not equal to each other. To assume they're equal to each other in all cases is a really bad idea. So we can set, and I'll give it a second for this to warm up again. We can, hopefully I actually started that. If I didn't, this is going to be unfortunate. I did, okay, good. We can let those porous, or we can let those resistances change. I'm a little bit on the fence if we want to use the same value, or if we only want to use like only inertial resistance and forget about viscous, or only use viscous and forget about inertial. There we go. For the sake of argument for this lab, what's probably the smart thing to do is we want to only change inertial resistance. It's going to be relatively sensitive because, again, it's proportional to velocity squared. So clearly, one case we want to run is going to be no resistance. I equals 0. This is going to be the full open flow rate. This fan is basically running as if you just put it on a table, right? There's nothing getting in its way. It's not trying to drive air through a filter or a sponge or anything else silly like that. It's just completely free flowing. It will move the maximum amount of air possible if I equals 0. What you probably want to do at this point is gradually step up this value. And I don't know exactly what value will be a good one for this fan, but as we gradually increase this, so we'll probably want to do like 6 or 7, let's say 6 steps. So the thing is, we don't necessarily know exactly what those steps should be. We need to figure that out as part of this process, or, well, we meaning everyone here, including myself individually. We can do that by looking at that fan curve that starts to show up. Because again, if I equals 0, that's going to be the maximum flow rate possible. And I know I literally just turned this back on. I'm going to turn it off again. If we have that fan curve and I equals 0, where on that curve are we going to be? Again, the curve may not look like this, to be fair. I'm drawing a fairly generic interpretation of a fan curve. But if I equals 0, where on this curve are we going to be? We're going to be literally, maybe not quite literally down here, but we will be as close to here as we can get. So we might be like here. So you might want to try changing I to something like, I don't know, 1. Probably not going to change it very much. It might move it just a little bit. You might get a point, exaggerate here. You might only move a little bit on this curve with that value of 1. Okay, maybe the next time you change it by like 5, then it might put you somewhere up there. Basically, you change it a little bit, see how far it moves you. Since we want to get some idea of everything between a volumetric flow rate of 0 and whatever this volumetric flow rate is, let's call it just the max value. If you start with I equals 0, you can figure out how much you should change the values to get an idea of what this graph looks like. As you make I really large, it will never quite get to 0. Will never quite get to 0, but it'll get close. If you crank I up really far, you might get really close to 0. You might get a point that's like up here on this graph. So realistically, what we want is, I think I said 6 points. 6 points, starting with 1 down here, and pick 6 others. And maybe you need to do more than 6 to get enough to kind of define the shape of this graph. But if you take big enough steps, if you make the first one really close here, you're not going to go very far, right? But with 6 points, if we put like 1 right here. 1, 2, 3, 4, 5, 6. You can conceivably get a pretty good idea of what this graph looks like. Exactly which I values you need to get these points, it depends. We don't know what the shape of this curve is. If we knew what the shape of this curve was, we might be able to make a prediction, but we don't. So you need to try several different I values to get an idea of what does this curve look like. The first one should definitely be I equals 0. That's a no-brainer. That's the minimum resistance possible. Maybe the next one, you want to try and crank it up really far and see how close it gets to this. And then pick kind of intermediate values to flush out what it looks like in the middle. Now, I said I values. For the intents and purposes of this one, we can just go ahead and forget about the viscous resistance. We can set that to 0. So you will have, by default, it's going to give you a very, very, very scary sounding name that really boils down to what I've already talked about. It's going to ask for inertial resistance in terms of what is called as, orthotropic tensor. Once this comes up, but what the hell does that mean? All it means is that it's properties in different directions that are orthogonal to each other. Fancy way of saying it was asking for the resistance in 2 directions that are perpendicular to each other. Resistance in X, resistance in Y. It kind of hides behind a relatively scary sounding name, but once you get the idea of what it means, it's not all that complicated. We can also change, if we look at porous inertial resistance, we can also change it so instead of a orthotropic, we can say isotropic. What does that mean? Iso means same, tropic means effectively, yeah, in this case, properties in all directions. Isothermal means you have the same temperature everywhere. Isobaric means you have the same pressure everywhere. Isotropic means you have the same properties in all directions. So we can say isotropic instead, and that gives us one value to change, which just means that the pressures in the X and Y direct, or sorry, not the pressure, this I term is going to be the same in the X and Y directions. So I would zoom in more if I could. I really can't, but we can just change this value to whatever the heck we want. Right now it's 0. We could plug in 50 and see what it does. So as a matter of fact, let's briefly look at what this vector scene looks like. If we tell this to run, oh, there is no, oh right, I didn't actually mesh it. And I fully expect this to give me a problem. So let me ask it to mesh, and we will see if this yells at me. I bet you it does. Although, to be fair, that would be 3-dimensional. Maybe it won't yell at me for 2 dimensions. Oh, seems to be fine. But this is just picking up where we left off last time, adding a mesh to that block. We added that block, and now we need to just put a mesh there so it knows what the heck to look at. So let me go ahead and open up a mesh scene so we can see what this entire thing looks like once this is done. And we can see that it has a mesh in this block here. We probably need to change a couple things though, because we don't need a mesh, we don't need a prism layer there, do we? The prism layer would agree really well here if we didn't have a prism layer across that boundary. So let's just go ahead and add, what was it, surfaces 6 and 3, I think, for our inlet and outlet. Yeah. Yep, 6 and 3. And we'll just ask it to remesh this really fast, and it theoretically shouldn't take very long. Let's see what this looks like. There we go. And hey, look, the prism layers agree exactly. You basically can't even tell where the boundary is. Like, I don't think you can see it up there. There is a very faint gray line that is right here. That is the boundary between these two regions. So it's an exact match across that, which is exactly what we want. Now, if we look at that vector scene, let me tell this to run for a little bit and add our outlet to this vector scene here. So we can actually see what the flow looks like through this tube area that we added. So let's add that block. And it's figuring out what's going on, but it's more or less just moving down the tube. Nothing fancy, right? Let me open up another scalar scene, and we're going to look at total pressure. Specifically, it does have to be total pressure and not static pressure or dynamic pressure. Any guesses why that is? Well, static pressure and dynamic pressure are related, right? How are they related? Flashback to middle of AE 160. If you change static pressure, what happens to dynamic pressure? If you change dynamic pressure, what happens to static pressure?
dynamic?
Kinetic isn't a bad word for it necessarily, it's just not the usual one. But yeah, static pressure and dynamic pressure equal total pressure. If you change one, the other will change, assuming you don't add or remove energy. That's Bernoulli's principle right there. If you do not add or remove energy from the flow, total pressure will be constant. Now, we are going to be removing energy from the flow or adding energy to the flow. We're actually doing both. We take this fan, zoom in a little bit here, and we're going to add a whole bunch of energy to the flow. This rotation adds energy. It's a little bit hard to see, but this is like a kind of a light orange right here. After the fan, it's a much darker orange. Total pressure has increased significantly, quite significantly actually. This is a little bit hard to resolve because everything looks orange. So let me change that color bar really fast and we can see how much it changes. It is significant. So where is my scalar scene? Scalar scene 1 probably. Yeah, scalar scene 1. So if we look at the scalar field, clip is off. So let's go ahead and look at like negative and negative 500 instead. There we go. That's a lot clearer. The error came in at, I don't know, it looks like about negative 250 pascals. And it's, or maybe that's just 0. It's hard to tell. Let's just make this 0 and see what it looks like. It came in at about 0 pascals, which is the boundary condition we gave it. It leaves with a hell of a lot more pressure than that. It leaves with on the order of 500. I mean, this is 520. So it's probably leaving with about 300 pascals extra total pressure that it didn't have coming in. So that delta P value, we're going to look at the difference in two things actually. We're going to look at the difference in static pressure. We're also going to look at the difference in total pressure. So change in total pressure and then also change in static pressure. Delta PT, delta PS. Technically, I don't need to write the S. If I just write delta P, I mean static pressure. But for the sake of comparisons, when we're talking about the fan curve and the delta P on the y-axis, you only still have to do 6 simulations, but you can measure both static and total pressure out of the same simulation and find the difference. But let me just go ahead and let this run for a little while. And it should gradually stabilize a little bit. Okay, that's stable enough for my purposes. To be fair, you should let it run a hell of a lot longer than that and make sure it actually is stable. I'm just doing this for the sake of demonstration at the moment because we don't have, infinite time to, or even, I don't want to sit here for 30 minutes and let this converge or whatever. So we'll just change it right now. But if we change our resistance, let's say I'm going to change this the currently isotropic inertial resistance from 0, no resistance, to 5. It's thinking about it. But theoretically, what we should see here is it is still moving flow through here. But we're going to have a drop in pressure. As the flow moves through here, its pressure is going to drop. Theoretically, it can make it all the way down to 0. this will also kind of have the net effect of increasing pressure there. But we can change by adding more or less flow resistance and then letting it converge. We can change the flow resistance. If we just left this tube open, we'd have no way of changing that, right? It would basically say that, you know, your pressure left here at some value and then it entered here at some other. Or, yeah, if we didn't have any type of resistance, we couldn't change delta P at all. It would just be stuck at whatever the heck it happened to be. If we do this, we absolutely can change it. So that was 5. I think it actually stopped running because it hit a stopping criteria. Let me change that. Yep, it reached 1,000 steps. So we could let that keep on running. Or we could also see, so right now, the highest, probably the average pressure, I'm just eyeballing it, is in the neighborhood of like, still 300-ish. We'd have to actually ask it to measure something to be sure. But we can change, I said we can change, there we go, our flow resistance. I just changed it to 2.5. And we will see that it's going to get a different delta P value. So we can change how much resistance it gets. That will change the delta P value. And we can also measure volumetric flow rate through this surface. So last but not, I guess let's try and measure a couple of these things and see what it looks like. I'm not going to look at all 6. We don't have time for that. We don't have time to let it converge fully. But we have time to measure a couple of things and look at what a couple of basic changes do to this. So how do we measure things in STAR-CCM Plus in general? Well, yes, but also no. That's not the whole picture. The report defines how we measure, or what we measure, and how we measure it. Monitor will actually take the measurement and store it. And the plot will let us visualize that measurement over whatever. So we want to look at probably fundamentally 3 things, I'm going to say for the moment. We want to look at total pressure, static pressure, and volumetric flow rate. So if we look at the mass flow average, we can look at the mass flow average total pressure in through the inlet. We can look at the mass flow total pressure at that interface. Oh, here, let me do this one at a time and talk through it. But we're going to need, realistically, I guess if we want to be thorough, at least 9 different reports. We want to take total pressure at 3 different locations. And we also want to take the static pressure at 3 different locations. And we also need to compute the volumetric flow rate at 3 different locations. So let's see here. I should be searching. So if we just search for total pressure, the important thing is we want to say total pressure in the lab reference frame, because total pressure relates to velocity, which is a vector quantity. So we have to be precise about what reference frame we want it in. But total pressure in the lab reference frame. So P total inlet. So we can select the inlet, which is going to be the air on the inside surface. We have our static pressure or our stagnation inlet. We can create copies of this to make our life a little bit easier. I'm going to say P total middle, which is going to be right here, is where we're going to measure this. For this one, it really doesn't matter which side of the interface you measure on. But I'm going to measure on the right-hand side of this interface. And then if we paste again, we can measure total pressure out as well. So if we look at the total pressure on the outlet, and we can do the same thing with static pressure. So I'm just going to literally copy all three of these and then rename them. Okay, so we have these three reports, and we can just tell it to look at static pressure instead of total. And I'm going to just make one plot with three things on it. So a single plot plotting all of the static pressures and all of the total pressures. So we'll have a couple different plots. Now, volumetric flow rate. How do we measure that? Any ideas? Anyone remember anything about continuity, AE160? Okay, mass flow rate's close. How do you calculate mass flow rate? Rho times V times A. Assuming velocity is normal to the surface and the surface is flat. It works out to this basic equation. So we can go at this a couple different ways. We could either divide through by rho, which gets us volumetric flow rate. It'll get us units of cubic meters per second. Or we could just compute the product of these two. So we could do this in a couple different ways. There is just straight up a mass flow report. We could just ask it, literally, how much mass flow rate there is. There is not a volumetric flow rate report. But we can also do something slightly different, because there is a general form of this equation. That's the simplified form. The general form involves integrals, but we also don't have to do the integrals. The computer can do it for us. Take back some real estate here. So if we want volumetric flow rate, we can get this as an integral over a surface of just velocity time, or velocity dotted with area times, well, velocity dotted with area, actually, that's it. So we can just take a surface integral of velocity, and it should get us volumetric flow rate. That's literally all we have to do. And what is the result of any dot product? Well, what type of value? A scalar value. It doesn't have any vector quantity, and volumetric flow rate is a scalar value. So what we can do here is we can just ask it, in theory, for the integral of, well, not velocity magnitude. We can ask it for the lab reference velocity, which is a vector quantity integrated over the surface. Let's see here. Is this doing what I want? Or even better, actually, we can also just ask it, since we know that the velocity should pretty much be well, actually, there's no guarantee that that's the case. Okay, maybe the surface integral isn't quite what we want because we need to make sure this does what we want. This is a little bit more advanced, but we'll go with it anyways. We can just define our own integral. If you don't have an expression to do what you want, you can make your own. So that's if you make a report that's under new user expression, this will let you literally just make your own definition. So let's see here. Is this what we want? Is there an integral here? Well, there definitely is a dot product, which is part of what we need. But I'm not seeing the integral that we want. So step out one level. We're still doing this the precise way to make sure we get exactly what we want, because we have no guarantee that the flow is going to be perpendicularly moving through any of these faces. Certainly not the outlet or that face in between. The flow can be moving at like 45 degrees to the face. It can be moving 45 degrees in one place and 30 degrees in another place. We can make no assumptions about which direction the flow is going. So we are going to make a scalar quantity field function, which we can define simply as what we have here. So this should have results of, well, here, where's the definition? We should be able to just define this as the normal to the surface dotted with our velocity. So velocity dotted with the normal to the surface. And then if we just take the integral of that, that is adding all of that up. So let's see if this makes any sense at all here. Oh, I don't want the expression. I do need that. I do need that surface integral back. User surface integral. And we ask it for our normal velocity, which it should integrate over whatever surface. So theoretically, volumetric flow rate should be the same if the flow is incompressible. This is probably pretty close to incompressible, but we want to make sure so we can measure this at different locations. So theoretically, we can measure the volumetric flow rate out, in, and at that other interface. And we can see what it looks like and if it's any different. volumetric flow rate out. Sure, volumetric flow rate through there, and then I'm misspeaking. This needs to be volumetric flow rate into the domain, and then middle is in between. Stator, there we go. Now, hopefully, this will make more sense if we just let this iterate some more and see what these values look like. So we have several plots here. Sure, we can plot multiple plots side by side. Where'd that other plot go? This plot. Let me make this as big as I possibly can, or we can still see what's going on, sort of. So we have, what is it? Static pressure top left, volumetric flow rate top right, total pressure bottom right, and just what the scene looks like at the bottom here. If you wish, feel free to get close temporarily. I'm just going to step through a couple of different I values, and we'll see how these graphs change. So if we change the inertial resistance here, right now it's 2.5. I'm going to set it back to 0. And also get this out of the way here. And we see some pretty noticeable changes in all of these pressure curves. And it looks like volumetric flow rate is trending up slightly. It's harder to see, but I just make this overall. Sure, why not? Oh, that is not what I wanted. There we go. So I changed it back to 0, and clearly volumetric flow rate is changing noticeably. It's going from, what is that? 1.7-ish cubic meters per second. I didn't actually tell it units, so it says it's square meters, but this should be cubic meters per second. To over 2 at this point. And that was a change in 2.5 of that I value. We could also change it to, actually, let's look at the total pressure plots. Let's see what's going on here. This is static pressure. This is total pressure. It's definitely not done converging, don't get me wrong, but it's very clearly changed quite dramatically. We had some change in total pressure. Yellow is the total pressure in the middle before the porous section. Red is the total pressure out of the porous section. Blue is the total pressure in, which is basically always going to be 0. So the flow goes through the fan, the total pressure increases a whole bunch, and then it goes through the resistance section and it drops again. How much does it drop? Well, it drops by whatever the difference between these two is. Right? It rose by whatever 0 to this yellow line is going through the fan. If we look at the volumetric or static pressure, it sort of has a similar relationship, except it's offset because the flow has a velocity. There is dynamic pressure. But it is still very clearly trying to figure out what the hell's going on. Again, because we don't have all day, I'm just going to change this to a much higher value of I, and we'll see what effect that has. This is 10, I think.
So theoretically, it's 25 would like almost acts as a rep.
Yeah, you crank that up significantly higher. Maybe it's 100, maybe it's 1,000, but yeah, if you make that higher and higher, it's going to generate more and more resistance. It will never quite be a wall. It will never completely seal it off, but it will get really damn close. So I don't know where this is going to converge, but clearly we have just reduced the amount of flow this has pretty considerably. It's already moving less than it was before, and that is still trending very noticeably down. Also, incidentally, why is one of these negative? It's rather it's going in versus out. Because if you take this dot product, which way is the area facing? Well, the answer is it depends. It always faces to the outside of whatever region you have selected. Always. Well, because you have an inlet on one side and an outlet on the other side, you can't make them entirely consistent. So one of these is always going to be negative, at least. You might have two of them are negative, one of them is positive. But there will be some amount of opposite signs going on here because just based on this dot product, it will compute a negative value for at least one of them. Because if the velocity is going that way and the normal is going the other way, this will result in a negative. If the normal is going the same way as velocity, that will be a positive value. So the flow in, and this goes for any mass flow rate, any energy flow rate, any volumetric flow rate, the flow in terms of vector quantities, is always going to be negative. The flow out is always going to be positive. If you do the vector math, that is just always how it works out because that's how vector math works. So let's try and formalize this a little bit. So with, again, at least 6 different variations in I, we want to generate a fan curve. We don't want to do it for 500 RPM, which is what I think I'm using here. We're going to do it at 2,000 RPM. I believe, let me double check that. Reference frames. How fast is our fan reference frame rotating? Now this is 1,500 RPM. We'll do 3,000 RPM. Definitely somewhat faster than what we're doing here. And again, I'll put this on canvas as well, but this will give you a little bit of a head start on people who weren't here paying attention, is that we want 6 different values of I. Including at least 0 and ideally one where volumetric flow rate is approximately 0, plus some others in the middle. So 6 different values for inertial resistance. Now unplug my laptop while it's running a simulation. That could end poorly. At a RPM of 3,000. The things we're looking for are static pressure. For now, I will include a subscript S on this, but generally, if I don't include a subscript S, I'm referring to static pressure. total pressure, and volumetric flow rate. Anything else you think might be interesting to look at for this sort of problem? What about density? Theoretically, this fan could be noticeably pressurizing the flow. One of these plots is static pressure. How much is it changing pressure? For the moment, it's probably not enough to matter, but at 3,000 RPM, it might be. This is changing the static pressure by top to bottom. It's probably 450 pascals. A standard atmosphere is 100,000, so it's changing it by about 0.5% currently. It might change it by a couple whole percentage points at 3,000 RPM, especially if the resistance is high. So think about what other quantities might potentially change. They're not going to be probably as interesting as these ones, but think about some other quantities, because I guarantee there's a couple of them that are worthy of at least looking at to see how much they change. Potentially, yeah. Now this is probably pretty thoroughly incompressible, so it's probably not going to change by much, but it conceivably could. It's something to look at. Or maybe that validates that this is incompressible flow. Theoretically, if this was a full-on compressor and not a blower-style fan, then yeah, it would change temperature. Generally, if you run air through a compressor, it does get noticeably warmer. As a matter of fact, that's precisely how air conditioners work. You compress the flow on one end, it warms it up, but then you dump that heat out through coils outside the building. And then you expand the flow again, and it expands and it cools down. And because you got rid of some of the heat outside, it cools down further than when you had it, when you initially compressed it. It's a basic heat exchanger cycle. So conceivably, temperature could be one of them. For lots of turbo machinery, temperature will change noticeably. Maybe not here, but that might be something worth validating. So we could also potentially look at mass flow rate. So mass flow rate, rho, and temperature could conceivably all change, although these are going to be less interesting than these three quantities. And that goes for pretty much anything unless you're doing a lot of compression, is that, well, theoretically, this should always be closely related to volumetric flow rate. Your density and your temperature are only really going to change noticeably if you have a really high power compressor or you're compressing air a lot, which some types of machinery absolutely do, which is not what we're doing here in particular. Your typical centrifugal compressor, not fan. They operate on similar principles, but they're optimized very differently. Your typical centrifugal compressor can get a pressure ratio of about 3. You can get about 3 times the pressure out that you feed into it. Your typical axial compressor gets you a pressure ratio of about 1.2, maybe 1.1, depending. You might get a 20% or 10% increase in pressure going through an axial compressor. So conceivably, for compressors or things of the like, you might get large changes in density, temperature, etc. We don't expect them here, but that might be something to look at regardless. So that's kind of the problem statement. And then you have the fan geometry already. Theoretically, you could already have a almost complete simulation set up at this point, with the exception of that resistance section. So this is, again, not quite the only way to do rotating machinery, but it's indicative of some of the ways that you would do it. Pretty much no matter how you simulate it, you need separate regions. You need to break off the part that's rotating from the part that's not rotating, and tell it to rotate at some different rate. Exactly how the math gets done can vary slightly, but the principle of it is the same. So that said, I've been yammering on for about an hour 40 at this point. So for the sake of my voice and also probably your ears, I don't necessarily need to talk over this a huge amount longer. Are there any questions regarding this? Not at the moment. Probably later.
So just to put all the pieces together, last week's recording and this week's recording, and then put them together and
Yeah, last week's recording was
building the
this part. This week was all about that part, adding the resistance.
and now we have everything to get the results.
Yep.
Okay.
The resistance is the thing that you're changing. I'm using to represent inertial resistance. And then depending on what the inertial resistance is, you'll get different behaviors of static pressure, total pressure, volumetric flow rate, etc. And actually you can see the very clear striations as total pressure is dropping through that area of flow resistance. Doesn't quite drop back to zero, but it does drop pretty far. So, in truth, let's maybe just to inform vaguely what's going on here. It was probably going to climb up to about 2.5, maybe even 3 for your volumetric flow rate, cubic meters per second at I equals 0 is according to the simulation at 1500 RPM. Again, you'll be doing a higher RPM, so it will not map 1-to-1. But this was about 3 cubic meters per second at an I of 0. At an I of 5, it was about 1.7-ish. It's dropped, and it's pretty rock solid, actually, at a value of a little bit over 1.1 for a I of 10. So theoretically, that I can still go up quite a lot without completely choking off the flow. But you need to vary I and see if we can develop something that looks like a fan curve. I'm just going to bump by an order of magnitude and see what it does. But we want to develop something that looks like a fan curve for this. To do that, we'll look at static pressure, total pressure, and volumetric flow rate specifically. And this, for reference, is I of 100. It's still obviously figuring out what the hell is going on, but our flow rates did indeed fall dramatically. They're down at like 0.36. An order of magnitude resistance increase dropped our volumetric flow rate by about a factor of 3. Maybe not quite that much because it's still stabilizing, but you get the idea. So even relatively large values of I, we started with 5, 10, and this is at 100 and it's still moving quite a bit of air. So that I value can go up pretty darn far before you completely starve this thing. Just as a vague idea, so you're not going in completely blind. So are there any other questions? Did people want help with following along with the simulation or anything else like that? Yeah. Correct. So we actually probably want to look at 2 different fan curves. That are typically plotted. One of them looks at static pressure. One of them looks at total pressure. But in principle, let me just redraw this, clean it up a little bit. In principle, we want to get a plot, actually multiple plots, but that is delta pressure on the y-axis and volumetric flow rate on the x-axis. We want to get at least 6 fairly widely separated points on this so that we have an idea of what this curve looks like. The thing I do not want to see is that we should be able to choke off this fan. If we crank up the resistance high enough, we get damn near 0. If we have a 0 resistance, clearly we're going to have something with a 0 delta P. So we can definitely get 2 points. Right? We You can definitely bookend it on either end by cranking I to a very high value and seeing, it won't quite be here, but it might be like here. Something very close to volumetric flow rate equals 0. Something very close to, the full flow volumetric flow rate. And then we want to get enough detail in the middle here so we have an idea of what this curve looks like. What I don't want to see is, you have 6 points that are all like right there. That doesn't tell us very much, right? Because we have no idea what happens over there if you do that. So, to some degree, the I values are up to your discretion, but this is what I do not want to see. I want to see a reasonable, they don't have to be uniform, don't get me wrong, but I want to see a spread that completely covers the range between full free flow, no resistance, and close to completely choked off. It won't quite be completely choked off, but you can get it really goddamn close. And again, by really goddamn close, I cranked it I up to 1,000, and it was still moving a fair bit of air. Let's see if it's resolved any. It's still moving about 1/3 of a cubic meter per second, so, or that was 100. Let me crank it up to 1,000 and see what it does. But anyways, check for multiple values of I, see what the delta P is, see what the volumetric flow rate is, and try and develop something that looks like a fan curve. It does rather look like that for a value of I of 1,000, it's like 1/8 of a cubic meter per second-ish. I'm just going to keep on adding zeros until it gets really small. But okay, like 10,000 looks like it might be enough to basically entirely choke this fan at 1,500 RPM. It's still kind of figuring out what's going on, but that's a really small number. So your bookends are probably 0 and about 10,000. Maybe 15 or 20,000 because you're operating at a higher RPM, but something in that general neighborhood. Again, we want something that's really, really close. So to give you an idea of what I mean by really close, you probably want to look for an I value so that this volumetric flow rate, let's call it the min value, is approximately, let's go with 5%. This should be an equal sign. V min is 5% of V max. Basically, you want to get this small enough. So if we started with a volumetric flow rate of 3, we want to get this down so it's at most like, I don't know, whatever, you can do the math. 3 divided by 20 in this case. Actually, let's go with 2.5%. You can figure out the math from there, but you want to get it not 0, but really small. Just to give you a little better idea of what I mean by really close to no volumetric flow rate. It will never quite get to 0, but you can get it really darn close. Yeah, this is like 0.03 cubic meters per second at this point, so you can get it really small. To be fair, 0.03 is a hell of a lot bigger than that. Or, sorry, a hell of a lot smaller than that number, because that would be 0.075-ish for what we have in this problem, but it gets you down to the right ballpark. That said, again, I think that defines the problem well enough that you have a reasonably scoped problem. Does that make sense about what the problem scope is? Does it make sense what the hell I mean by 6 different values of I, such that we don't wind up with 6 data points that are redundant? Questions, comments, clarifications, concerns? Any of the above? None of the above?
So then instead of multiple fan curves, one for total pressure and static pressure, both be
Right, so you'll have at least two of these graphs. One will be total pressure. One will be static pressure. So you will have effectively two graphs. One which will have the y-axis of a change in static pressure. And then the second one is a change in total pressure.
would that be the difference between the input and the output?
No, yes and no. This is the change. Let me see here. This is a good point. Generally, the thing that this looks at is the change in static pressure from, after the fan to the outlet, I believe. So let me clarify. So we know that the pressure should come in at a total pressure of 0. We had a stagnation inlet. Give this a second to show up. That'll take a second to warm up. But we know that the total pressure came in at effectively 0. That was our inlet condition, right? That's a number we gave it. It shouldn't be anything other than a total pressure of 0 as it comes in. When it leaves, it's going to leave with some amount of total pressure. But when it exits the fan itself, it's going to have some different total pressure. So what we're really looking for is, if this is 0, we're looking for the total pressure drop, or the pressure drop here, across this section. Because the pressure came in at 0, it rose by some amount, and then it's going to fall by some amount, but it also leaves with some amount of energy. Right, we can't discount how much energy it leaves with, so we have to just look at how much this resistance generates. Right there. So we're looking at the delta pressure across primarily this, but we should measure it at the inlet as well to make sure we know what's going on. So again, delta pressure across this outlet resistance section is what we're looking for primarily, but you should measure it at the inlet as well. That is an important part of this. And just to sanity check it, this is what, if we zoom way out, we can see what the step function looks like for this, because we started again about 1.7-ish. This probably would have made it up to 2.753 or so at a resistance of 0. Resistance of 10 was like 1.1. Resistance of 100 was like a third. We had a resistance of 1,000 very, very briefly. It looked like it was going to land somewhere around 1/8. And then a resistance of 10,000 brought us all the way down to like 0.03 cubic meters per second. So you will probably have a graph that looks very much like this, and you want to basically let it converge and then change the resistance. Let it converge, change the resistance. Let it converge, change the resistance. Probably starting at 0 resistance and then increasing it until eventually you get to one that's really low flow rate. And then you can, pull off the value. You can pull the values off of these graphs in order to record actually what that fan curve looks like. That'll let you put the different points on the fan curve that's hiding behind this and figure out what should you expect from the performance of this fan. And, it actually seems to work reasonably well at moving air from the looks of this. Now this is 2D. What's the limitation of that? how does it get a volumetric flow rate if it only has 2 dimensions? It assumes the z direction is 1 meter. So, to be fair, this is not a small fan. You know, the fan is a foot across and a little bit over 3 feet long. So this is not a small fan, but it is moving quite a lot of air. So, in that context, that number does make some amount of sense. But that said, I think if people would like help with the simulation, we can do that at this point. If not, then we can go ahead and wrap up for today. But again, do not forget that resistance section. That is what lets us actually figure out what this fan curve is. If you don't add that block on and are able to add resistance to this thing, you can only really get 1 data point, which is not enough. So go ahead and ask any questions or whatever. I will stick around for, as long as anyone's here to ask questions or get help. And other than that, I will post the assignment on Canvas, but you guys have the details. You can go ahead and get started on getting data now.
We're only at 10 slides. Yeah. I'm not getting to less than 10 minutes. So maybe
If you go over, it's not going to penalize you.
I'm sure penalize me.
Oh yeah.
I don't think we're exactly.
Or no, she may actually just.
Are you
You're
gonna
like
fly
full
me?
class.
Okay, so I feel like the first 5 you can do it. First 5.
Yeah. Well, were you talking about the Gmax?
Yeah, because
stuff?
I'll go up to the GMAT section and then
I'll wrap it up with that.
yeah. I'm not worried on this. If she has questions, yeah, I'm gonna look at them.
Thanks for it.
Yep.
Bye, Professor Andre. Bye. Can we do a view?
Sorry, what?
Oh, can we do a view? You said if we wanted to, we can stay in. You said we could do a view. It's just changing the eye, right?
I mean, realistically, I don't know how much more we could do because it already has changed several of them. But sure, why not? Oh. Actually, let me,
So
before I
just to
forget,
confirm, you said just add you need a block and add resistance.
hold on a second.